Excel sheet, it's a lot easier for us. Okay. It's a lot easier for us to see what these numbers are going to, because you have to understand that unbounded growth is not all equal. Sometimes something's going to grow faster than the other, and you all have to know function behavior to know which one, as you're riding those out to positive infinity, is getting larger and larger. Like looking at the first function here, what's the order of the functions when x is equal to 1? Well, our biggest one is c, and then that's followed by, who can tell me, I guess, what the order would be? Then a, and then, all right, so you said, we started off with c, then a, and then what's the next one? H, all right, followed by? G, and then aren't F and D the same?
Yeah.
Okay, and then finish with D and E?
Yeah.
Okay, so is that the order of the function values constantly throughout?
No.
No, watch what happens. So the growth rates are very much different. The next one, when it happens for 10, and then the next one, when we get to that, you could list out what those answers are for the next two. But notice these numbers start getting really, really, really big. Like e to the 10th, take a look at b. That's going to be a huge number. I think that that's the largest one, right? b is the greatest when x is 10. Is that correct?
Mm-hmm.
Yes or no?
Yes.
Yeah. When we go to 100, though, is it still the biggest one? Which one is the biggest one? E is going to start getting huge. Now, let's figure out what happens as we go out to positive infinity. So, let's pick a number of x. Let's say we'll make it, okay? So we picked a huge number, and watch what happens. These numbers here are so big that they won't show in our cells unless we start making them really big. Oh, there we go. You've successfully created an overflow error. So let's try one that maybe isn't so big. Let's do 5,000. Okay. Now, you can see there's only one that's going to result in an overflow error. And you can go through. Now, which one is the smallest one? F. Which one out of these would be the biggest one? E is going to be the biggest one. That causes the overflow error, followed by 206 here. That's 206 times you've moved it over. That's how gigantic it comes out to be. So understand that they're not all the same. So at which point will they no longer change? And at which point, what are the functions, which functions change positions at that point? You have to go through and tinker around with what your function values are as to when this stops changing. And you need to find when the two that are growing the fastest are equal to each other. And I think that we can agree which two were the ones that are going to grow the fastest, or which two functions are competing to be the largest. Hands up, please, if you can tell me. Taking a look at what you've got there, which two are competing to be the largest as we go out to positive infinity? Or which ones, as we go out to positive infinity, have the fastest growth rate? We've got two people, seriously? What do you want to say? Would you say D, E, and G? No? I see two that are growing a lot faster than that. What's that? E and B? E's gonna, or sorry, not E.
And E are supposed to be.
Oh, sorry, I misread the columns, I'm sorry. So this column here, which would be E, along with what's the other one? That's getting huge? The G function, yeah. I'm sorry, I was looking at the headers on the top. So that's what they should come out to be. And this is a real easy, test for you to see. Not all growth rate is the same. And especially think about a log graph. If you were to go through and graph out a logarithm, over the course of time, like an exponential is going to look something like this, a cubic would look something like this, this is going to be linear. A log function, when you look at it, shoots up really quick down in this region. This would be a parabola. X to the 10th is going to be big. This function, when you graph it, is going to look kind of like that log function in D. So you have to understand the growth rate of them is not the same. All right? Now, set that to the side, and have your note packets out open to where we left off previously. We have today, at the front of our packet, we'll go through and fill in what the expectations and what we're going to hopefully bang out. We are today doing day 4, so today we're going to fill in on 9/12. What's due next time we meet? That limits A sheet. And I'll tell you right now, you've got to make sure you give it your best effort. Who has stopped down? Raise your hand if you've stopped down to see Miss Coit at some point for help down in math. That's terrific. Was it a good or bad experience? Did she curse at you?
Oh.
Did she take her shoe off and bang it on the desk?
Yeah.
No. Listen, and in all seriousness, I was talking about it with somebody, 2 people from the current Hall of Fame members. And I said, what do I tell them that makes the biggest difference? And they said, to use your language, if you're going to be a schlub, you're not going to be successful. You have to make, their point was, if you make it a priority, you'll be very, very successful. And there are people from last year looking at the marks that you get a 95 in pre-calc. What does that mean? It means you're good at following directions. Now we're to the point where if you get to get a grade of a 90, you have to understand that calculus requires you to get all of the algebra right and understand a different concept. It's not just, plug and chug. Do you understand the concept? If it looks different than what you've done before, do you shut down and say, I don't know how to do this? Or do you go through and try something new, and then check to see if it works? The other end of it, too, is there's some of that stuff that you have to look up. And it takes you literally go into Google and type in, that first question, right? What do, absolute value graphs of those manipulations look like? If you're stuck and it's 10 at night, Google it. You literally, you act like the only thing you can do is go to, what's the, Schmoopies or something like that for English, where you copy the notes out. Spark notes, right? That's the only thing that she's in. Use it for math. Go in and say, I struggle with the derivative. What do I have to go through and do? I struggle with the absolute value. What is that going to look like? Or, in this case, absolute value graph examples. That's what you type in and see what it looks like. Because there's a whole mess of stuff. And you click till you find what works. And if that doesn't work, you come in and see Miss Coit or myself. But there always ends up being this subset where we're going, well, I couldn't do it last night. We didn't give it to you last night. You've had it since day 2. So make sure you go through and get it done. Now, we left off a couple pages ahead. We left off on day 4 stuff, I believe, and we got through squeeze theorem last time. Now we're going to talk about limits going out to infinity. The other thing is, you all very seldom, do you go through and read something to describe mathematics. Go through, please, and read this first paragraph here. And make sense of it. You're probably going to have to read it more than once. Looking at what's there, it says the concept of limits as x approaches infinity means the following. What happens to the y value, which is the output, as the x gets infinitely large? So what are the function values going to as my input starts getting huge? We're interested about what's happening to the y value as the curve gets further and further out to the right-hand side. That's positive infinity. You can also talk about what happens as you go to negative infinity, which is going to be over on the left side. This means what is happening to y values further and further to the left, terminologies that are used. Now, the one thing that Ms. Miller doesn't do that I do is every time you're given an infinity, I ask that you put a sign on it. The Math Excel won't ask you to do that, but I do when you give it out in here. So if we're talking about a positive infinity or infinity, they mean the same thing, and we're always going to put a sign on it. So these limits, these terminologies we use are that, and these limits tell us where blank asymptotes occur. Well, those are going to be horizontal asymptotes. You're looking at what's happening to a function as it goes out to the left and to the right. If anything happens, the curve can go up forever. In this case, the limit doesn't exist. For convenience, we say that the limit as it goes to positive infinity does not exist, or DNE. Now, there's another way that you could say this. You could also say that it goes to positive infinity. The limit itself doesn't exist. It goes to positive infinity. They mean the same things. Now, this is my caution to you. On the AP exam, they go for this. The reason why is because they say as something goes not to a number value but to infinity, you can go through and say infinity as well, because you're opening up a generalization pattern. Understand that this means that your function will be unbounded. And as we go out to positive infinity, does this have a horizontal asymptote? No. It's rising forever. So what's happening as we go out to the right, and that's why you need to know those parent functions, because as I go out to the right, it's going to positive infinity. It's not leveling off ever, it's rising forever. The curve can go down forever. In this case, the limit doesn't exist. Now, you can say that the limit does not exist, or you can go to, since it's telling you it goes down forever and we're working with infinity, we would say negative infinity. And again, this is unbounded, and I guess you could say it's unbounded above. And over here, this would be unbounded below. You also know that this would have no horizontal you can go through and say that these asymptotes go to a value if they go through and approach a line. If they're asymptotic to a line, that means they're going to approach a value. If we look at this function, in this case the limit as it approaches infinity would be this. Now let's take a look at this one here, and let's call this first one a of x. So what's the limit as x approaches positive infinity of a of x? Hands up please if you can tell me what that limit would be. What's our limit as we go out to positive infinity? Perfect. However, the end behavior on the other end is going to be different. Let's look at the limit as x goes to negative infinity of a of x. Hands up please if you can tell me what that's going to go through and give you. We've got 3 people. What's that? What do you want to say? -1, that's terrific. Let's call this next function b of x. So I'm going to say the limit as x goes to positive infinity of b of x. Hands up please if you can tell me what that's going to equal. It's more than one answer we'll take. What do we say? You could make the argument for 0. Does anybody else have another one that they were thinking? Because there's more than one way, I guess you could see it. Like I'd say a half or a third, as long as we can come to consensus. The first one we got was 0, so we'll state that it's 0. That's fine. Now over here, we don't really know what this is going to precisely because there's some pixelation on the graph. But we could say that the limit as x goes out to negative infinity of the b of x. Let's say that that levels off at -2. By the way, it can go through a horizontal asymptote. It can't go through a vertical one. You can dip below and ride back up to it. It just depends on how we define the function. Questions on that? Let's take a look then at the next one. The curve can level off. The limit is x goes out to infinity is a value. So see how these waves are going through, they're oscillating, but eventually if we were to track this out to infinity, it would go through and level off to the same value. Let's call this c of x. So I would go through and say the limit as x goes out to, now this case, see how it converges to the same thing? I can condense that and say positive or negative infinity of c of x. Who can tell me what that limit value would be as I go out to positive and negative infinity? We got one person, we'll wait for 5. 2 of us, 3, Molly, what do you want to say? 0. We can go through and this we would say is bounded, meaning that there's an upper and lower max of this. This has a horizontal asymptote. That horizontal asymptote would be y equals 0. Now here's what another thing that you've got to understand, and I touched on it when we talked about the last one. It can go through a horizontal asymptote because like we said, here's our horizontal asymptote. Is it going locally through? Is this graph going low, or is my c of x going through the horizontal asymptote? Sure. And eventually it's going to keep going through and it's going to level off to a value of 0 over time if we extend it out to infinity. Questions on that one? Let's go over to the next page. Now, there's a bunch of, let's say, shortcuts that I'm going to ask this. When you do this out, we ask that there's sometimes we'll just use some logic, but there's sometimes where some of you may have been shown some rules for limits to infinity if it's a poly over a poly or some rational expression with an integer exponent over another one. We ask that you go through when you need to and use a dividing out technique. Take a look at this first one here. What is, well, in pre-calculus you learned the rules for limits going out to infinity, where f of x is a rational function according to the degree or highest power of the numerator and denominator. That's the comparison test. These only work for rational expressions involving polynomials. That's the problem with them, and that's why last year I didn't go through and show them to people. These only work for polys. In calculus, we're going to encounter a lot of different types of expressions. You've got to be able to go through and consider the end behavior. It's simpler, and it makes you look at the function. What's happening is I got really, really big in terms of the numerator, then the denominator, and then the function as a whole. So as we go through, the end behavior model of these is going to be what's driving the behavior. Now, when we're doing this, the end behavior model for this is the term of highest degree. So we'd say that this would be 2x cubed. That's what's driving the behavior. Everything else is latched along for the ride. Look at the next one. And by the way, it's not the first term, it's the term with the highest exponent. Or the term, the degree is the highest exponent. So our degree in the next one is going to be 3 because this is my term with the highest exponent. So what's driving that second piece is that there. Now, when we talk about creating an end behavior model, you're asking, as we go out to infinity, what's driving the numerator? And if we're looking at what's driving the numerator, that would be this expression here. What's driving the denominator? That expression there. So as we go out to positive infinity, we say the limit is x goes out to positive infinity of 2x cubed over 7x cubed. Nothing else, I guess, and maybe sometimes you'll see like a dot, dot, dot after because there's other garbage there, but it's not affecting the end outcome as we get cubed. Looking at this, what do we know about the growth rate of this expression? What's it going to level off to as we go out over time? 2/7, because what you're going to end up noticing is this is 2 times a number cubed over 7 times a number cubed. What reduces out of this expression entirely? the x cubed, so that leaves you with a 2 over 7. You're going to have a horizontal asymptote of y equals 2 over 7. So it depends on how you want to view it. This is your limit value. This is the end behavior model. That's what models it going out to infinity. Now, sometimes the left and the right end behavior are going to differ. If you go through and do this differing out, here we have one where we have an absolute value in the numerator and an irregular expression down in the denominator. Looking at what's there, we have to go through and consider a couple of different things. Think about what's going to happen. Well, let's do this. Looking at the numerator, we'll say this. Here's our end behavior model. This would be the limit. As x goes out to positive infinity, I'm looking to see what's going to govern this function or drive this function as I go out to positive infinity. In the numerator, I would be left with the absolute value of 2x, because that 5 that's there is just really going along for the ride. What's driving the behavior in the denominator? The 3x. Now, what is this going to as we go out to positive infinity? Hands up, please, if you can tell. Play around with some numbers. Plug a 2 in. Think about what happens if you plug in a 10 or 1,000. What is this going to get really, really close to? Hands up, please, if you can tell me. Track this out to infinity. We really have 4 people. Look at MIT. Not really. No one can tell me? Think about what this is going to. The numbers get huge. Because the numerator, I'm plugging in like 1,000. The denominator, I'm plugging 1,000. This would simplify down to just be 2/3. Now, the next one is similar but different. And I want you to see if you can process what would happen to this limit as we go out to negative infinity. So go through and do the other end of that right now on your own, please. Tell me what they think this is going to go to when we go to negative infinity. When we got 3 of you. Play with plugging in some big numbers. Remember, you're plugging in now not 1,000, but negative 1,000. Negative 5 million. Why would it be negative in this case, Tom?
Only the denominator would be negative.
Yeah, the numerator is going to give me a positive number. But the denominator now is going to be a negative number. If there was an absolute value down here, this would still be positive. By the way, if there was no absolute value here, would this go to positive 2/3 or negative 2/3? If there was no absolute value in the numerator, positive. That's terrific. Now, we've got to keep in mind our relative growth rate. So what's our right end behavior model of this? Well, if I'm looking at this, what is going to be affecting things more? The x or e raised to the negative x? Which one of those is going to govern things more? I'm going to say the thing I'm going to be most concerned about in terms of what's growing fastest is this right here, e to the negative x. Because that's going to be what's going to sort of govern our behavior as we go across. What is e to the negative x the same as? E does come from the natural law. No? It's e to the negative x power. What? 1 over e to the x. that's going to help us decide where this function is going. Now let's go through and evaluate this as we go out to positive infinity. Looking at what I have, I'm going to separate this up into two different limits. That's from our properties the other day. I list out the limit as x goes out to positive infinity of the left half of the binomial of x. Then plus, and maybe we'll do this, the limit, that's a notation thing, you've always got to end the argument of the limit. The limit as x goes out to positive infinity of, this would be 1 over e to the x. Let's see what these things are going to, because there's two different limits to infinity that we're going to take. Looking at what's here, if I go out to infinity, what is this limit going to? Positive infinity. What is this going to? Someone said it. It's a 0. It's going to be a really, really small value. So in terms of evaluating out this limit, I go through and say, this is the same as infinity, positive infinity, plus a 0, which would give you a final answer of positive infinity. What is that doing as we go out? It's going to positive infinity. Now the next one's going to be a little bit more awkward. What's the right behavior model? Or sorry, the left-hand behavior, we did the right-hand one before. Again, I go through and need to see this rewritten out. This is something awkward that we're going to have to deal with. This is the same as 1 over e to the x power. So let's evaluate it now going out to the left-hand side. This limit would be the same as the limit as x goes out to negative infinity of x, then plus the limit as x goes out to negative infinity of 1 over e to the x. Now let's evaluate what these are going to. As I start plugging in gigantic negative values, what is this limit going to go to for the first half? Negative infinity. Now, here's the other piece that you need to keep in mind. So that goes to negative infinity. Plus, what is this going to? And it's going to be tough for you to conceptualize it. You're close. If I plugged in positive values, that would be a huge number. Like if I were to take the limit as this goes out, and let's say I plug in like e to the 5,780, blah, 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 all of those digits, right? This would be 1 over that amount, and this would get really, really close to this denominator. Is it getting big or small? It's getting huge. So what's 1 over a huge number going to be? Essentially 0, a small number. Now, here's the only problem. Now I'm going to change it up ever so slightly. I'm going to make it, this is 1 over e to the negative. I don't evaluate that out right away. What needs to change about this, I guess? And I could ask this to an Algebra 1 student. They should be able to tell me the same thing. Where does it need to go? It's going to go up to the numerator now. So what is this side going to? What's this limit going to? This is going to be plus a positive infinity. Now we have to ask ourselves this. So you've got two things pulling the behavior of this function. You've got an x and an e to the x, because negative of negative e to the x and e to the x. Which half is growing faster? Part with the e to the x. So which one is sitting in the driver's seat? Which one's governing this limit behavior as we go out to infinity? This right here. It overpowers the other part of it. It renders it insignificant. That's how strong that growth rate is. So what's the final answer that we would give? Nope. It's not a 0 because they're not balancing each other out. Which one is weighing heavier on the scale? Yeah, the e to the x is going to lead us to being a positive infinity. That positive infinity value is much bigger than the negative infinity. Because keep in mind, even if I'm at like negative 5,000, this is only negative 5,000. This would be e to the 5,000th power, which is going to be huge. Now, let's have you all, we just have this to finish. Go through right now and let's make some suppositions. Go through and try this last group for me. Now, let's go through and start analyzing what we're going to have happen here. Who can give me what they think is going to happen with any of them from 1 to 6? Some of them are much easier than others. You tell me which one you want to do. Go ahead. Okay, what'd you get? This has a horizontal asymptote then at y is equal to 2 over 7.
5.
Let's take a look at 5. Now, 5 is 1, and I love 5 because you've got to really think. Were you thinking this is the memorize or die one?
I think it's 1.
It's not going to be 1. The memorize or die is 1 because if the limit is x goes to 0. That's the memorize or die. But this should be easy stuff. You're not going to think it is because you're not used to analyzing what you have in front of you. What do we know about the output values from sine? Tell me what we know about the output values of the sine function, the range of the sine function. We got 3 people, 4. What do you know about the output values of sine? That's terrific. So let's get that, jot that down to the side, that we know that this is always between -1 and 1. Now knowing that, consider what's happening as we go out to positive infinity. Can anybody now take a guess as to what they think this function's going to? Why? Or what else could it be? Yeah. This is always going to be some number between -1 and 1. Or sorry, those should be brackets. Between -1 and 1 over some huge value. Now it's not huge because more is getting done with it, but if we pin it between those values, the numerator is always a small number, the denominator is huge, so this would work out to be a limit as we go out to infinity of 0, and we would say we have a horizontal asymptote of y is equal to 0. It's leveling up. Now this would oscillate, it would bounce up and down, and it would be the one that we saw before where all of a sudden those waves are going to get much, much smaller. How about for either, I'll say this, you may even struggle with 3 or 6, and that's all right. How about with 2 or 4? Can we be a risk taker on 2 or 4? It's 3 people. Noel, what do you want to say?
For 2, I said 0.
2, you said 0, and I would say you're right. Can you tell me why?
Since it's hitting the third and the bottom will be moving faster, I just want to keep it similar.
Yeah, what's driving what's happening in the numerator?
It's x squared over 2x in third.
Which one is driving in the numerator?
Squared.
Just the x squared. And then in the denominator, you have what?
2x in third.
2x to the third. Which side is growing faster? Which side has the stronger growth rate?
Denominator.
The denominator. So again, it doesn't matter what the numerator is. Infinity cubed is going to be bigger than infinity squared. So this would have a horizontal asymptote, by the way, of y equals 0. Now, I guess let's deal with 4, because I hope 4 is an easy one for us. We got one person. I'm so sick of already dealing with somebody. I'm disgusted. We got 4 people. We. For 4. Why? What do you want to say?
Well, isn't it like a really big number?
Close. You could. It would be like infinity over e to the infinity. Though. So let's keep that in mind. It's e over e to the infinity. So who can tighten up and give me an answer that you can justify?
In the numerator, it's a linear growth, but in the denominator, it's exponential growth.
So which side's growing faster? There you go. So I go through and state, well, this right here is going to be linear. This right here is going to be exponential. So that means that this would come out to be 0. You'd have a horizontal asymptote of y is equal to 0 because the growth rates are different. An exponential going out to the positive infinity is going to be huge. Now down here, this is one thing that you all struggle with. When I take the square root of something squared, that's the same as the absolute value of my number. So we might want to list this piece out here. Someplace on your paper, you're going to want to list out the square root of x squared is the same as the absolute value of it. Of course, to be the principal root. Now, looking at that, who can tell me what they think this one's going to go to? Play it out with big, big numbers.
1.
Why is it 1?
Because in the bottom, it's going to be x. It's, when you like solve it out, it's going to be x over x.
I list this out as the limit as x goes out to positive infinity of x over the absolute value of x. That's why it is what it is. That's what's governing the behavior. But we do want this step shown here so you understand what's going on. Now, who can tell me what our next one's going to be? Let's finish up with number 6. We've got 1, 2 of you. What do you want to say?
-1.
Why?
Because,
How would you rewrite this? Let's start off with that in our sort of truncated version.
x over the absolute value.
So the limit as x goes out to negative infinity of x over the absolute value of x. So far, that's terrific.
The bottom goes to be positive here, and I have just 1 negative, which is
Now, and this is one thing that, this is not judging, but we need you to understand this. When you're taking, because you all are taking, well, this course is geared to the AP. Again, I don't know if they have like a session where they explain to you what the course is, what your AP courses are. You're allowed to take this for just trader credit. You don't have to take it for AP credit, and you don't have to take it for MCC credit. Find out who here, just raise your hand if you have a vague idea of what college is, or like a short list of colleges you'd like to go to. If I'm you, I get in touch with what those schools are to find out what they want you to take. Because you may want to take both, you may want to take neither. There's a scholarship for the MCC component of it. You can apply for it. You say, I love MCC, I love the Xerox company because they're the ones that give the money. Say, oh, it's the greatest thing since sliced bread. It's wonderful, I don't care that Xerox fires people all the time. It doesn't bother me in the least. Wonderful, go Xerox, I love MCC, etc. Fine, lie, who cares? The scholarship, you all should lie all the time. You lie to me constantly. Now, you want to decide what works for you. The AP is very rigorous, and that's what we're talking about. Or that's what we're gearing the course for. Understand that when you go through and you take the exam, you have to pick the option that works for you. But in terms of being successful on the AP, you have to use your words, which means when we talk about things, it's not that or this. Get rid of, what are those pronouns that take the place of nouns? Is that right? Okay, we don't use pronouns, we use actual words like nouns, like numerator, denominator, radicand, exponential, etc. Because if you're not, the down and dirty on it is this. Okay, not